So you want to know more about organocuprates? I know that you do, or you wouldn't be watching this video, and I'm getting ready to tell you more about organocuprates. Alright, so it's going to take me this video and maybe a second one and possibly a third one, depending on how fast my little feet can move through these example problems. So I want to talk about organocuprates and what to watch out for in the world of organic chemistry. So organocuprates. In the last video, this is where we ended up. We said cuprate is in reference to cuprous or cupric, and cuprous or cupric is really our copper. So we are going to be looking at organometallics that have copper involved in the structure in some form or fashion. The problem here, though, here's the problem. Poor little copper. Poor little copper thinks that he's so big and bad that he's going to come to this fight and he's going to get there by himself and he's going to have a pep talk with him. And he's going to say, looking at himself in the mirror, "You got this, you got this, you got this." But when copper begins to show up, he realizes that he can't do this alone. It's a little puny thing. And this little puny thing is going to show up to a fight behind the school building with this crowd of boys or maybe girls. There's no way. There's no way Copper's going to do this on his own. So Copper needs some backup. Copper needs to be able to call a buddy. And Copper needs to say, "Hey, I can't do this by myself. You're going to have to show up to this fight with me. You're going to have to show up to this organic because I can't do all of it on my own." So he reaches out to his best friends, and the best friends are also in the world of organometallics. Well, the two that we've talked about so far, there's only been two, has been lithium and magnesium. And folks, one of those Copper's pretty close with. And Copper calls upon lithium when he can. "Hey, lithium, I'm getting ready to go beat somebody." I'm not telling you to go beat somebody behind the school building, but this is my analogy here. So a chain is going to have to start to form. Copper is going to show up, but he's not going to show up on his own. He's going to have some backup. And that copper is going to show up to this fight in the world of organic chemistry with his buddy. And this buddy is going to be lithium. It's going to take two to tango. It's going to take two for this organic reaction to go forward. And because of that, this is our first what we call a coupling reaction. Now, you can regard coupling reaction as these two metals coming together. However, a coupling reaction also couples two pieces that are carbon-based, ding ding, together. Because we couple them up, right? We take this piece that didn't know the other one. We take this piece that didn't know the other one. And we bring them together. And we say, "Go get married, have some babies, come back and let us see your organic products." Well, copper and lithium is going to be able to do that job for us. But copper and lithium also has to be coupled in order for this to go forward. So this is what we are going to call our very first coupling reactions. And really, it's because we are connecting two carbons together. So once more, just like before, we are referring to a chain elongation reaction. That's kind of what we're doing here, folks. All right. So we've seen our first chain elongation way back in Orgo 1. And that was with this acetylide ion. That's what that one was for. And then our others were the lithium and the Grignard reagents. All right, so here was our first, the acetylide. And then we brought in some lithium compound. And then we brought some Grignard in that was able to basically join these carbons together in merry matrimony, and then they went off on their own to create a longer carbon chain molecule. So now we're looking at another. And this other one are copper-based reactions and our first coupling-based reactions that we're going to discuss in this lecture. All right, so just like MGBR, Yeah, we can call this an organomagnesium bromide, right? I mean, that makes me sound smart. Whatever. That's not what we're into this for. We want to know basics. However, if I'm working with these copper organics, there's different names that these things can go by. We could Corey Posner. All right, well, that's one way, but I'm sorry, that's a little bit more effort than just calling it kind of copper and our lithium organometallics. Corey Posner's no better. Well, there's another one called Whiteside's House. Corey Posner, for some reason, makes me think of a sitcom back in the 80s. I don't know. Whiteside's House, I think of applesauce. Maybe it's just the weird little name that comes along with it. We don't really use that name either. Corey Posner or Whiteside's House, whatever. Give me a break. Give me another name that we can call these things. I mean, I don't want to call them copper, lithium, organocouplers. No, that's not what we're after. Corey Posner. No, don't want Corey Posner. Whiteside's House. No, what we're going to call these instead is something called a Gilman. So when we refer to Gilmans, we're referring to a copper-based reaction. When we refer to Grignard, we're referring to a magnesium-based reaction. You got to be really careful because both start with a G. Folks, I know. Grignard and Gilman. Why do they both start with a capital G? That's just the way organic treats you sometimes. So you're just going to have to be able to keep them separate. So Grignard is magnesium-based and Gilman is going to be copper-based. Well, there's other terms that we need to throw out here. We need to learn words, right? We need to learn the terms of organic chemistry. And copper and lithium couplers, also known as Gilman reagents, we can refer to them as a dialkyl. All right, so alkyl basically means a carbon chain, right? And di means two. So we've got two of these carbon chains on a lithium cuprate, on a lithium copper based foundation. Okay, so here's the thing with Gilman. This is why we start with lithium and magnesium first, because the Gilman reagent actually has to be prepped most of the time as well. We've talked about how to prep the lithium compounds, right? We take this alkyl halide, we react it with 2 moles of lithium, and we put it in a proper solvent, and we get these lithium organometallics. And then we talked about the generation of the Grignard, and we said MgBr. Okay, so we take an alkyl halide and we react it with magnesium in the proper solvent, and we get these MgBr molecules that come along that we can do things with. Okay, well, that's great, whatever, but we need to focus on Gilman. We talked about the preps of those two, so why shouldn't we talk about the prep of the Gilman? We have to, because once again, these things you don't order most of the time. These things you make as you need them, as you need to use them. So it's very often part of the process, folks. That's why we have to go through the prep of these organometallic compounds. So this is how we do it. Normally what happens in the prep of the Gilman, we're going to have an organolithium reagent. Oh, I see. Look up here. We've already talked about a lithium orgo reagent. That's what we first started off with. So lithium compounds are great. In a laboratory, we rarely ever do that lithium type of compound and go forward with it. Grignards are a little bit better to use. But if I did make that lithium, folks, this has to be the first starting ingredient to make the Gilman. So not only could I take this alkyl lithium compound and undergo a reaction with it, but I could also take this organolithium compound and now pair it up with a copper. And this copper is going to be in the form most of the time with copper iodide. So copper iodide, think of as a salt like sodium chloride, right? You've got a positive piece, you have a negative piece. It's an ionic compound. So I'm going to take this alkyl halide and I'm going to react it with this copper iodide salt, basically. And I need a little bit of solvent in order for this to go forward. Well, if you take a look at the magnesium bromide solvent, it's really the same thing here. Copper's got some set of electrons that need to be satisfied. We can't just let them float and do whatever they need to do. We need something to stabilize this with. And what we use are really the same solvents that we use for Grignard. And that is THF or, okay, there's the big or, simply ether. And this is exactly what we used for Grignard when we talked about the Grignard examples. So when this goes forward, when these two things react, we are going to get what we call our coupling reagent, and that is going to be a copper and a lithium compound. And that R group is going to be doubled. I know, just bear with me. Just bear with me. Okay, give me a few minutes and we'll flesh this out a little bit. So let's talk about kind of the mechanics before we go further. I've got this lithium compound maybe in my flask. It's a lithium halide that I maybe just recently made. And we've talked about how to make those. And now I throw in some copper iodide salt. And that copper and that lithium are both metals. They're both metals. Copper behaves kind of like magnesium here in a sense. Do you remember what happened with magnesium? We had this alkyl group with a halogen on it, and we threw magnesium in. And what we did is that magnesium kind of went in, sandwiched in between here, kicked us off. That bromine was going to go away, and magnesium said, whoa, wait a minute, don't go nowhere. I need you. And then whoop, back around it goes. So if this was a bromine, which is what they normally are in the halogen world, magnesium squeezes in, pop, off it goes, and magnesium reaches out really quick, grabs the bromine, and brings it back in to create the Grignard. And this is our MgBr unit. Copper kind of does the same thing here. Copper does something very similar to magnesium because this is what happens. Transmetallation. You remember that word? We just talked about it. You should remember that word now. Transmetallation means we switch metals, and we switch metals because of the electronegativity values. And if we can get a metal that's closer to carbon's electronegativity value, then these reagents become a little bit more stable. So this carbon that is bonded to the lithium looks at the lithium electronegativity value, and then it looks at copper's electronegativity value, and it says, ooh, I really like copper a little bit better. And the reason is because that electronegativity is very close to mine. So I think that we could come into a relationship, and I think that we won't argue as much. I think that we'll get along pretty well. I mean, now I know we're going to have some issues, but we're not going to constantly be arguing. So it makes it a more stable product because of that. So transmetallation begins to happen here. So this R group says, ding, ding, bye-bye lithium. And copper is the new man or woman in town. So we get this copper kind of group that forms. But the same thing that magnesium did, copper's going to do. And it's going to go, whoa, 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 no, wait a minute, lithium. You're going to come back. And I don't need you to go anywhere because I kind of like you too. Oh gosh, drama every time we turn around. So when that lithium comes back and it pairs up with the copper, and that pairs up with the carbon of the organic piece, we form what we call the Gilman reagent, and that's what this Gilman reagent is. But folks, it's going to bring two alkyl groups to the picture. In order for this to form, two of those alkyl groups will have to show up to the party, and they will have to be there as well. So think of this almost like copper taking up one of the alkyl groups and lithium taking up the second alkyl group. Now, here's the story with this. No one freaking knows what goes on here. I can't give you a mechanism. And the reason that I can't give you a mechanism is because the mechanism is not fully known. We just know it happens. So no one said organic is completely solidified. No one said that we had a concrete foundation to work on. Most of the time we do. But there's going to be times like this where we really can't fully explain every step of the mechanism along the way. So we just have to be okay with not knowing curvy arrows. And I think that you are perfectly okay with that idea, because that's less curvy arrows that you're going to have to memorize to regurgitate on a sheet of paper. So I think that's going to be okay. We also need to kind of understand what we just talked about. We said that we have this R group that's now bonded to this copper. And the R group, we've talked about bonding to lithium, and this R group, we've talked about bonding to magnesium, and we've talked about this concept of transmetallation. Well, because these are closer in EN values, then that means that these are less reactive than lithiums and magnesiums. And sometimes it's a very good thing. Sometimes we don't just want to put our hands on the flask and give it a little bit of heat for this to go forward. We want this to be maybe a little bit more stubborn, a little bit more stable, so that way we have more time to do the things that we need to do with them. So less reactive is not a bad thing sometimes. And I think that's important to say, because a lot of people forget about that kind of topic. All right, so overall, let's kind of just recap here just for a minute. Let's say that I bring in CH3Li. There's my lithium-nated compound. I need 2 moles of this stuff. And I'm going to react this with copper iodide. And I'm setting up my Gilman. Okay, now this is just making the Gilman. Notice we haven't said anything. Well, what happens to the Gilman after we make it? You don't know that yet. We've not talked about that yet. We will in just a second, but not right now. So if I take the alkyl with the lithium on it, and I mix this with my copper iodide, I form a Gilman. And that Gilman is a copper lithium compound. My Cu and my Li, well, boom, there you go. They make a couple. And then what they do is that they don't let this other couple go either. There's 2 of these for a reason, and that's because that alkyl group that lithium was carrying, well, I'm going to bring 2 of those to the party as well. So we got a group of 4. It's like 2 couples. 2 couples madly in love. 4 people, 4 beating hearts. And they can't really make up their mind on which one they want. Whew, that's a soap opera right there. That's a soap opera. So this copper lithium is our Gilmans. Now we have to know what to do with it. Okay, this is making it. We talked about how, again, to make the lithium orgos. We talked about how to make the Grignard orgos. And this is how we make the Gilman orgos. We take a lithium that we've already talked about. We mix that with some copper iodide. And then we form this copper-lithium complex in a way that carries with it 2 alkyl groups. So now what happens is that this Gilman reagent, the R group that is contained in that compound, is going to act as a nucleophile. Just like always, just like before. Every time we've talked about nucleophiles, folks, it does the same thing. Nucleophiles are negative. They look for a positively charged carbon. When they find the positive charged carbon, they can go in and substitute. They can maybe go in and try to help eliminate. They could go in and add on to the molecule, blah, 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 blah. Same stuff. No difference. Nothing new here. Nothing to see here. Go home. So this is the difference, though. It's how to get to this point. Because up until now, we've always talked about nucleophiles in terms of negative OH, negative NH2, negative sulfurs. You get my picture. These were always negative pieces that we have discussed, and we said these were nucleophiles. These go in and attach positively charged carbons, and bloop, 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 and bonds break and bonds form. The same thing's going to happen now here. But you need to look at this as a CH3 group that just carries a negative. And we treat it just like all the other nucleophiles that we've always treated for every other organic reaction that we've ever talked about before in Orgo 1. There's no difference here. So, let me prove my point. Let's say that we bring in CH3, CH2, 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 Br. And now we add a Gilman. Oh, what Gilman, you say? Okay, well, let's do a CH3, CH2, parentheses 2, CuLi. What product is formed? That's what the question's going to say. What product is formed from the 1-bromobutane reaction with the Gilman reagent shown below? I mean, that's what they're going to say. Okay, they're trying to make this complicated. It doesn't need to be complicated. I can't ask you to draw curvy arrow mechanisms, so I'm never going to ask you to do that. We need to know point blank what happens. Well, you know how I operate. You know how I'm going to work. What I'm going to do is I'm going to start off with this reagent up here in the front. CH3, CH2, CH2, CH2Br. That is what they give me. And they say react this with Gilman's. Well, okay, not a problem. The reason that it's not a problem is because this bond is what it always has been. Bromine is the electron sucker. It's electronegative. There's the negative. And this carbon is slightly positive because of that. And I just told you, look at this. Right up here, this Gilman provides a nucleophile. That is why we use it. And that nucleophile is going to be a negative carbon this time. That's the whole point of this lecture series. It's not positively charged carbons. They're negative. So here is a negative piece that needs to be added on. Okay, well, where does that negative go? It doesn't go to that negative bromine, does it? No. They're the same charge. They're going to repel each other. They hate each other. So this negative piece is going to go to that carbon that's partially positive. Okay, so what that means is that down here in our reagent, the starting reagent that they give me, away goes the bromine. That bromine disappears, and now this opens up a site of attachment to that positively charged carbon, and that piece, folks, it's the piece that's inside of the Gilman. It's what we have two of, but we don't need two of them. We just need one. We just need to add one to the molecule. That's it. So that CH2 right there, that is going to be the start of the connector, CH2, and then off of that will be CH3. And there's your product. That's all there is to it. Nothing more. Now, you're probably saying, well, what happens to the other ethyl group? Okay, well, if you are asking that question, good for you. That other ethyl group pairs up with the copper because that copper is a positive 1. Bye-bye. And away it goes. So we get this ethyl copper that forms. Well, what about the lithium? Okay, well, that lithium gets spit out as well. And that lithium is positive. And that lithium and this bromine is going to see each other and then away it goes. All right? So these two pieces, my copper and the remaining R group, there it goes. Away. Bye-bye. We don't need it. We don't need to calculate that into our product. We're not interested in that. So off it goes, and we could care less about it. And now we have this lithium and this negative bromine. Lithium's positive 1, bromine's negative 1. I've got what you want, you've got what I want. Let's come together and there it goes. We don't care about that either. That's not the product that we're after. The product that we're after are the two alkyl groups that are coupling. This is a couple reaction that are coupling together to make a new carbon-carbon bond. That's what all of this is about. Now, what I've done is I've left off a solvent in order for this to work. This solvent, again, THF, pretty common, pretty standard. That's my cupcake molecule. Or something like ether would also allow this to work as well. So I do need some type of solvent that I can mix with these two, and that solvent will be my jacuzzi, so I can get these two compounds to kind of break the ice, notice each other, come together, and make me a product, baby. All right, so let's take a look at another one. Let's say I've got this carbon double bond carbon. Oh gosh, what is he doing? He's making these double bonds. And anytime this happens, we know stereochemistry is coming along. That's right, so stereochemistry is going to happen. And let's bring in my Gilman. All right, so CH3 and CH2, and let's just keep the same. No big deal. I mean, we worked with it first, so we'll work with it again for this one. There we go. So we've brought in this alkene. But this alkene, folks, remember, the only thing that we said that we needed here was some type of R group, random carbon-containing group, with a halide. Right? And that meets this criteria. There's no big deal there. I mean, it meets that criteria. It looks a little complicated, but it meets the criteria. And then we have this Gilman. All right. Well, you're going to love Gilmans. If you've not noticed it already, they're pretty easy. What? How is anything this easy? Okay, well, let me show you. I'm going to take this compound, no matter how nasty it might look, and I'm going to redraw it, because I always start with my reagent that they give me. There it is. So they want me to take blah, 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 and add blah, 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 blah to it. And they want me to know what type of product. They want me to provide the type of product that gets formed. Okay, so here's how you do it. Find your halogen right there. Get rid of it. And now we're going to replace that halogen with the R group, folks. It's inside of the parentheses. CH2 and CH3. There you go. There's the product for the Gilman. Is that hard? No. It should not be hard. But let me give you a quick review, because I know this could have been a while since you had Orgo 1. And even if you did have Orgo 1, you might have had an instructor that never talked about stereochemistry. Shame, shame, shame on them. So let's talk about how to name this. My longest carbon chain, 1, 2, 3, and 4. So this is a butane. All right, so there's my butane. But it's not really a butane, is it? Nope. And the reason is because I see a double bond. So I'm going to have to get rid of the ANE, and I'm going to have to put an ENE, because that represents alkene, and alkenes are double bonds. Well, where is that double bond located? That double bond located is at carbon number 2, so this is a 2-butene. And that 2-butene is in a certain type of position. Can't really call it cis. Can't really call it trans. And the reason is cis and trans are really supposed to be used to compare hydrogens on both sides. Now, I do have a hydrogen to the left, but I don't have one to the right, do I? No. So we can't use cis and trans. What we can use instead, though, are things like EZ. And this is where I told you in Orgo 1, the Z nomenclature, Z groups are on Z same side. So that's kind of like a cis. So let's take a look at these carbons, and let's kind of figure out if we have the E or the Z form based on how I've drawn it. So I look at this hydrogen, and I look at the carbon. That's what this particular carbon's connected to, an H and another C. Carbon has a higher atomic number, so therefore this carbon gets the higher priority ranking. And then over on the right-hand side, I've got this carbon, and that carbon has a bromo group, and that carbon has another carbon. So the higher atomic number is going to be my bromo group, so that is the highest ranking of that system on that side. So these two highest rankings are on opposite sides. They are not on the same side. And because of that, they are not Z. They are E instead. So this is a E2-butene reacts with a Gilman reagent. And these reactions come together to make a product, and we need to name the product. All right, well, if I look at this product, my longest carbon chain, 1, 2, 3, 4, 5. So right here is the longest carbon chain that I need to pay attention to. So this is a pentane, but it's not an A. It is an E for the same reason as we just described. There's a double bond that's in there. So pentene. A number closest to the end where that double bond's located. So from the left, it's the second carbon in. From the right, it's the third carbon in. So I have to go this route, 1, 2, 3, 4, 5. So on carbon number 2, I have my double bond, 2-pentene. However, on carbon number 3, I have another group. And this carbon 3, because I didn't get to circle that, right? That was not part of the long chain. Up here it was. That was part of our longest chain. There was 4 carbons there. Down here it was not. So on carbon 3, I have a methyl group. Same as before, what kind of priority gets assigned here? Not a big deal, not a problem. Hydrogen or carbon, carbon has the higher number, so that's higher priority. Over to this side, carbon and carbon is a tie. I move on. Carbon and this one runs out. So this would be my high priority on that side. Once more, these are on opposite sides, and they are not on the same side. So that means that this is an E. So here's the thing with Gilman's. I've just showed you that Gilman's preserves the stereochemistry. So E2-butene reacts with this ethyl lithium copper Gilman reagent. A coupling reaction happens. That coupling reaction in this case is going to produce 3-methyl-2-pentene. That stereochemistry is going to be preserved. So it is still the E form of what was there before. It simply goes, the alkyl halide, the halogen simply goes off, and the alkyl group goes on in its place. All right, so that's where I'm going to stop this video. So in the next video, we're going to pick up here. We're going to do some more examples with Gilman. I think that maybe with these first 2 examples, you're going to be like, this isn't too bad. This is pretty decent. I think I can handle this. And if so, I hope so. Because once again, that means that you're doing your job. And that also means that I'm kind of doing my job too. So if you didn't know what Gilman was before, you now kind of know what Gilman is now. And it's simply finding the halogen, erasing it, and replacing that halogen with the alkyl group. That's as complicated as it needs to be. So in the next video, we'll pick up with our examples and we'll continue on, and we'll get a little bit more complicated maybe as time goes forward.